Before I give her a formal introduction, I just want to remind you that there will be a seminar next week. So a week from now, our next speaker will be Amanda Lindu she's a postdoc from Carnegie. So for today, our speaker is Dalia Kirschbaum. She's currently a research scientist at NASA Goddard, so she's really not far away in Greenbelt. Dalia did her undergrad at Princeton and then her PhD at Columbia. So her PhD work was mostly about landslides and remote sensing. So after her PhD, she was a MPP postdoc. So that means she was a postdoc from the NASA postdoc program. Not surprisingly, at NASA Goddard. So that was also a while ago. So soon after that, she actually was employed by UMD. So she was at ESSEC for half a year or so?
Yeah, like 5 months, I think.
5 months at ESSEC. So I just learned this today that although she was employed by UMD, but today is her first time being at UMD campus.
Yes.
So I'm very, very excited that I took the chance to invite her to come over and visit us. So her current work is mostly about collecting global scale data set to understand the process and then to monitor natural hazard. So the data set is mostly about precipitation or satellite data that you can detect landslide or to see landslide or see the formation during the time. And she has been spending a lot of effort on compiling some global scale inventory. She also has some website about that. I think she might be showing you guys. Also, I think she's gonna mention that in the talk. I wanna just promote that she's actually very interested in working with seasoned scientists. So including if you are undergrads or interested in working on like mapping from Google Earth and doing some global scale catalog, you can definitely contact her. Okay, so I'm gonna pass the time to Dalia. Please welcome her.
Thank you. Thank you so much. All right. Well, thank you so much for inviting me, and I've really enjoyed speaking with many of you actually today thus far. So it's a pleasure to be here, and so I'm going to be talking on a topic that I think maybe some of you know a little bit about, and some may not know much. But I'd like to give you kind of an overview of where I am, what I'm doing. It's going to be fairly high level, but I'm happy to go into details in any part of this. If you raise your hand and ask questions, we can save them till the end. But anyway, I just want to give you that kind of overview of where we are. So just some acknowledgements. I have several different colleagues that have been supporting or working on this research, and my photo credit is me. So this is up in Alaska, where we were visiting the glaciers in Juneau, and very rarely do you actually get close and personal with landslide-related pictures. At least when you're dealing with remote sensing data, you pretty much just sit in your office. But just to give a very quick overview of who I am, where I came from, I grew up in Minnesota. This is me at 10 in Kennedy Space Center. And as was introduced, I kind of went through and studied geosciences at Princeton. My PhD really focused on how we can take remote sensing data and apply it to natural hazards, and was able to segue that into a postdoc program where I was looking at landslides but using remote sensing and land surface modeling to understand how we can incorporate and understand landslides in a broader scale. And then I became a civil servant in 2010. And so I think I had a privilege of talking with some of the graduate students over lunch and just highlighted the importance of doing internships to kind of get to the next stage of what you're doing. So just to highlight here that the NASA intern program is for undergrads, high schoolers, graduate students, and really encourage you to look into that, as well as the NASA postdoctoral program, because these are excellent opportunities to get your foot in the door and learn more about what's done at NASA, among other places. So just one more slide about what I do. So I have a lot of different hats actually right now, which is really fun. This is the picture I'm most proud of from working at NASA. So this is me, full suit, in a bunny suit, we call it, standing in front of the Global Precipitation Measurement Mission. I'll actually show you some of the data from that mission, which was launched in February of 2014. And so for research, I take that data as well as other satellite and ground-based products to understand landslides with a real focus on getting a kind of broad picture, global or regional perspective, and look at how humans, anthropogenic changes, as well as even climate are changing the patterns in landslide activity around the world. And I'll give you kind of some previews into that work. I also do quite a bit of outreach, and that's why I was in the bunny suit, is I was doing an interview in front of the GPM satellite, and so working with K through 12 audiences and engaging people about how GPM data and other satellite data can be used for lots of different applications, not just landslides. Another one of my hats, which was pretty prevalent last week and continues this week, is I'm one of the disaster response coordinators for the agency. And so in that role, I work with a team across the different 10 NASA centers to bring different satellite assets, in situ data, and other products to bear when there is a disaster. So we coordinate with groups domestically, such as FEMA, internationally, like USAID, and some of the other international NGOs, and in-country partners. And so we have a lot of different relationships to try to provide satellite data, which is free and open, from NASA to these different partners. And then lastly, I have a role in kind of strategic leadership and leading different efforts, applied sciences, for a while, but specifically I'll talk briefly about the CEOS landslide pilot, which is kind of an interesting source of collaboration for remote sensing data. So just a really quick outline. I'll give you some overview to kind of get everybody on the same page as a Landslides 101, specifically with respect to remote sensing. I'd like to talk a bit about what we're doing with respect to modeling, mapping, and monitoring. And then where are we going? Talk a bit about what I see as kind of the potential path forward, and hopefully get some of you to participate. All right, so we really love graphics at NASA, so I have a lot of graphics. So let's start with landslide overview, just so we're on the same page. I primarily focus on rainfall-triggered landslides. And so what happens there is you have your driving forces, you have the resisting forces on the hill, and the factor of safety can be estimated when the resisting forces when the driving forces are larger than the resisting forces. And of course, there's all these different other elements. You have rivers that are undercutting the toe of these landslides. You have roads that can destabilize some of the slopes, and you also have trees or devegetated areas where that can also have kind of a confounding impact on landslides. So while they're typically observed at the local scale, you need to really understand them at a bigger picture. So one, why landslides? Why not some other hazard? Well, of course, in terms of landscape evolution, landslides are geomorphologically very important to move sediment. And so there's all these different kinds of processes. When I talk about landslide, I'm really referring to pretty much all mass movements, but just 101, what we generally refer to as a landslide is the first part of the first part of the event is the type of material, the second part is the movement. So rock, avalanche, landslide, mud, flow. You get a sense of kind of how to characterize them. That's kind of the general pattern. In terms of why we should care, they're pretty pervasive around the world. They happen in nearly every state, nearly every country, and they cause way more fatalities than people realize around the world, mostly because very few people are actually cataloging those fatalities and impacts at the global scale. And as I said, they kill people. This is just one example, but not a rare example where, people are building up into the slopes. I was just in Rio last week, and you see the slums that are being built right into the steepest, most vulnerable slopes. And so we have to understand where and when these landslides might happen on natural environments, but ultimately how it impacts humans. Okay, so where are they? So this is a database that we've been compiling for the past 10 years, and I'll go back to this at the end of the talk. But in order to understand and model these processes, with any physical process, you need validation data to improve or to validate your model. So we've been compiling a catalog of global rainfall-triggered landslides since 2007. We have, it says 95, I need to change that. We have over 11,000 reports now, and this data is widely accessible to the public to use in research. But you can see the distribution, the size of the dots and the color indicate the number of fatalities. And so what quickly jumps out is, yes, the US has a ton of landslides along the Appalachians, Colorado, along the West Coast, but the terms of fatalities, these are the areas where we have the most impacts in terms of loss of life. When are they happening? Well, generally they tend to happen during the Northern Hemisphere monsoon season. So during the monsoons and also the tropical cyclone seasons in the Northern Hemisphere. And then this just breaks out the landslides by country. The way that we've compiled this data is through primarily media reports in English. And so there's a huge bias towards the US. About 29% of our inventory comes from the US. Whereas if you look at fatalities by country, India and then China rank as the most catastrophic. But these are also biased by two huge events that happened, one in India and one in China, that really dwarf our understanding of how many fatalities, thousands of fatalities for one or a collection of events. So this is really to give you an overview. Now, why should we model this at the global scale? Landslides inherently are a very small process. Most of the time they initiate kind of at the size of this room and they can run out for kilometers, but ultimately they're a small process. But using Earth observation data, we can actually get a global perspective. And the reason we need that is because there's no global or even national monitoring system for landslides, period. There's nothing. And so what we have, for example, with tsunamis, we have a global tsunami warning network with different buoys. We have our global seismic network. For hurricanes, we have GOES satellites that can monitor our entire world routinely, all the time. And then we have our hurricane monitoring sites around the world that are pulling in all of this different satellite data to observe hurricanes. We also have databases for fires. University of Maryland has a very well-known one. But we don't have landslides. So we're trying to move that nozzle a little bit forward and give that big picture perspective. So why am I doing it at NASA? Well, NASA has a very strong Earth science department. NASA's goal is to look at all planets, including our own planet. And so this shows the different missions that are in formulation, in implementation, in current life, and then extended life. So there's about 24 satellites or instruments that are designed to look down at Earth and measure different Earth processes. And so the vision of NASA is to reach for new heights and reveal the unknown, so what we do and learn will benefit all humankind. And so along those lines, we have the big Earth science questions that we have at NASA, such as how is our global Earth system changing? What causes these changes? How might they change in the future? And how might they affect us? And so in all of those, that's what we're trying to address, how landslides might relate to each of these big questions. All right, so I promised some more graphics. And so the way that we do that is through an Earth observation fleet. I don't know how many of you keep tabs on what's going on with NASA, but we just launched ICESat-2. Yay! On Saturday, it was successful. We're really looking forward to seeing how that data is going to be used to measure the height of our ice caps and our glaciers. It's going to be a very important observational record for understanding long-term change in our Greenland glaciers as well as in Antarctica. And so what you're seeing here is some of the different orbiting satellites. They have different orbits for many different reasons. They also have some constellations. So what you see here is Cygnus constellation coming around, which is looking small satellites looking at surface wind speeds. You have polar orbiting satellites as well as the A train, which is looking simultaneously at the same place, taking different measurements from precipitation to air quality and the like. And the way that we do, one example, I just threw this in like a minute ago, is to look at the different processes that govern how different disasters can impact humans. And so the mission that I work with, the Global Precipitation Measurement Mission, GPM, is just one of the constellation of sensors. And so I just wanted to highlight this because it's just really cool. But this is a pass of Hurricane Florence as it was starting to intensify. And so what you're seeing here is a three-dimensional view of this hurricane as it was just becoming a hurricane. And so what's particularly cool about this image is that you have this kind of anvil shape on top. And so what this is actually showing is that there's these really strong winds in the top, the top of the hurricane. There's a little less strong winds at the bottom. I'm oversimplifying this, but basically the discrepancy in the winds is causing this hurricane to kind of get blown apart. But what we observe with the three-dimensional structure is once those winds die down, the hurricane is actually going to rapidly intensify. And the way that we can see that is by these really hot towers, so these big, strong convective systems in the middle of this storm. So if you bring that together with wind speeds, with precipitation, and different ways to model sea surface temperatures, we're able to study not just hurricanes, but the Earth as an integrated system. Yeah?
Quick question. Can you go back one slide?
Yeah.
What are we actually, I guess the little colored dots, what are they actually, tracking?
So that's precipitation.
Precipitation.
Right. So if you look,
like little droplets of water.
Correct. So it's a graphical representation. It's not like the actual drops.
Yeah, of course, yeah.
But what this is showing, so the light green is light rain to red purple is heavy precipitation, rainfall, and then the blue and the ice, the blue and the purple on top actually represents the melting layer of this storm. So this is all the snow and ice that happens on top of every hurricane. Sorry, I didn't describe it.
Oh, thank you.
Yeah, so this is all snow and ice. And actually with GPM, we were able to observe snow at the top of hurricanes, which you don't think exists, but this is the first time we could actually observe that because of the active radar on board this satellite. Cool. Yeah, keep asking questions, especially about GPM. I could go on for days. Okay, so in terms of studying Earth as an integrated system, this just highlights some of the different observations that we have as well as the model products. And the reason that I'm showing this to you is to make the point that it's not just one observation that we need. It's not just, we don't just need precipitation. We need to look at the soil moisture, the land cover change. We need to look at modeled data such as precipitable water or clouds, even looking at sea surface winds to really understand and understand the system as a whole. And so this takes me to remote sensing for landslides. So in terms of the processes we can use to understand what's happening with landslides, this is just kind of a cartoon highlighting some of the data. So as you saw, we had heavy precipitation. We can look at satellite observations or model data. We can look at the triggers, such as snow melt or snow accumulation. We can actually map landslides using different types of wavelengths. So we can use optical data. We can use synthetic aperture radar. And then, of course, there's other triggering sources such as earthquakes. And then this really important element, which is what happens when landslides hit things and understanding it in terms of infrastructure, loss of capital. I'm not going to go into that, but it's actually an area that we're moving into now, which is really exciting, which is actually risk modeling in the true sense of the word. So really understanding the vulnerabilities of an exposure of populations to landslides. And just to get a sense of the types of remote sensing platforms, it's not just taking a picture from space. You have optical sensors here. You have synthetic aperture radar, which can provide different clues into the deformation of the land surface to landslides in different ways, which we'll talk a bit about. And then, of course, you have other variables, the geomorphologic variables as well as the atmospheric ones that can help us to understand precipitation, soil moisture, and other exacerbating factors such as burned areas, land cover change, or snow. All right, so moving into methodologies, I wanted to kind of phrase this in a couple different ways. I wanted to talk about some of the work we're doing with mapping, some of the work we're doing with modeling, and then monitoring and more. Apparently I'm into M's today. Maybe because I'm at the University of Maryland. I don't know. So first, to go into mapping, to understand how we can map. Obviously, I'm coming from NASA. I want to see how we can do this from a remote perspective. And so the processes that we can that we can look at are looking at the who, the how, the what, the when, the where, and looking at the landslide cycle and seeing what types of observations can be relevant to these different parts of the landslide cycle, monitoring, rapid mapping, and characterization, both before the event, during the event, and in the recovery stages when I put on my disaster monitoring hat. And so how this works is first, looking at displacement mechanisms, we can use synthetic aperture radar to look at slow-moving landslides. We can look at optical data or image tracking to really understand where these landslides might be on a landscape. Then, of course, when we need to understand the triggers that occur, where is similar to how, but also understanding kind of the distribution and how to get kind of cohesive and robust inventories. And then how can you fuse these data sources? Because as I said, there's not just one answer. There's multiple ways to look at the problem, and you want to try to bring as much data as relevant to bear for these issues. All right, so in terms of mapping, there's a lot of different ways you can map landslides. You can do it with airborne, and NASA does have a strong airborne component. Right now, actually, out of JPL, the UAV, the Unmanned Aerial Vehicle synthetic aperture radar is being flown over the flooded areas in Florence to understand where there might be where the standing water might be, where they could pre-position or position supplies for the recovery efforts, and that data is being used by FEMA and others. So in terms of airborne, there's a lot of different applications. In terms of in situ data, obviously we really need to have ground-based observations to validate what we're observing from satellites, to calibrate and validate our algorithms. We have the commercial data, such as Digital Globe. So we have partnerships or working agreement with the Digital Globe to have access to high-res imagery to do some of the mapping. And then lastly, the satellite data from NASA, which is this is an example of the California landslide, and looking at using Landsat to monitor change over time of that huge event. Another table, sorry, but this just gives you a sense for those that really are excited about satellite products, the different types of products that are available, some of which are for pay, and some of which are accessible, like Landsat and Aster. And so what I wanted to digress here very briefly was to talk about the role that we are playing with the Committee on Earth Observing Satellites, CEOS. And so I don't want to take too much time because I'm not quite sure how relevant this is to the group, but more of an FYI. The Committee on Earth Observing Satellites represents every space agency in the world, and we get together to talk about there's different working groups on concepts related to capacity building and water, et cetera. And so I actually co-chair a landslide pilot under the disaster working group, working with the head of the landslide hazard program at USGS and others. And so the goal is to kind of increase the use of satellite data for landslides in particular, but for the disaster working group for disaster risk management, and use that ultimately to inform policies, decision makers, stakeholders, et cetera. And so really quickly, in terms of the pilot objectives, we really want to move things forward to understand how we can best utilize synthetic aperture radar and optical data to understand landslides. And this is an area that is really emerging for research. So if anyone is interested in a research project relating to the intersection of these types of products, this is really I say a really new area with a lot of new data to be exploited. So if that piques your interest, please talk to me. And then also it's to kind of see how this can go throughout the risk cycle. So in terms of the regional study areas, we've focused on Nepal and the Pacific Northwest. And also we have secondary study sites in Eastern Africa, the Caribbean, and China. And those are the leads for those. And so I just want to give just a very few results as to what we're doing with this data to kind of underscore what's happening. So the first is in Nepal. So Nepal was hit by a pretty tremendous earthquake in 2015, and it happened more over here. But what we're doing is trying to map some of the landslides in these really, really remote areas, such as the Karnali Highway, that you're dealing with slopes that are extremely steep, roads that cut through halfway through the slope, and landslides that continually, every monsoon season, block traffic for weeks. And the weird thing is that, not weird, but there aren't any consistent inventories over that region. So Landslides happen every summer, every monsoon season, yet we don't have inventories. So one of the first things we've done is actually map landslides using the high resolution optical data over the Karnali Highway and these other 2 highways to get a sense of what the distribution of landslides might look like. And this data has been useful for the World Bank because they're actually developing a mitigation program for the Karnali Highway to try to improve the mitigation of this highway, but they don't necessarily know where to focus. So what we've been doing is using, a little bit hard to see, is using high resolution data available through the commercial vendors as well as through CNES in France to look at multi-temporal views of landslides through time. What is the cause of these landslides as we go throughout time to understand what the major triggers might be, the size of these landslides, and how they might impact the roadways. So this is one example. Another one, and I know there was somebody in looking at machine learning and potential automatic detection, is this is work by a colleague at University of Strasbourg in France, and it's looking at using automated detection of potential landslide in Nepal to look at what happens, the earthquake happens, then the monsoon hits, and what happens in subsequent monsoon seasons, so the 2016, 14, 15, 16, 17. How does the landscape recover from a major earthquake? And so what several different teams are doing is trying to understand these processes geomorphologically, what is the recovery of the landscape after there's been coseismic landsliding, and what are the relationships between the seismic activity and where there was the most shaking with the predominance of rainfall. And so if this is an area that interests you, I also have a project for you. All right, another example of mapping is done by our Landsat data. And so this was done by some developed students, and I'll make a plug here. NASA has a developed program, which is for students and others that have just graduated to do 12-week essentially internships at NASA, working with a stakeholder and a NASA scientist to apply a remote sensing concept to a specific end user. So this was the group working with me, and they developed this automated landslide detection process using Landsat over Nepal to be used by some of the groups in Nepal to identify landslides. So the develop program, if you're interested, is a great way to get your foot in the door and learn about a remote sensing technique or concept in a really meaningful way. All right, so I'm going to give a couple more examples of just moving from optical data to synthetic aperture radar. Synthetic aperture radar, it sends out an active signal, you get it back, and based on the type of change you can get between different overpasses, you can start to see change or deformation in the events. So this looks at landslide, the Jur landslide in Nepal, again, using some Cosmos SkyMet data. And what you can see is the left shows this landslide deformation, and the right shows the interferometric coherence. And so, in general person speak, what we're trying to do with this and here is to understand changes in how you can, when there's total cloud cover, synthetic aperture radar can see through the clouds. And so what can we observe by looking at a stack of images over time? And so this is just work by David Beckert, who's at JPL. And so what you can do is by being able to look at all of these different images in a stack, you can start to see changes in the deformational structure of a mountain. So for example, this just shows a specific area in the Trishuli Basin. And what you can see here is there's a big blue blob, for lack of a more technical term. So you can get a sense now, now we've identified some blue blobs, right? So we've identified that there's been a pretty decent displacement. Well, what does that represent? And so what we're trying to do is now couple this type of identification of movement with optical imagery that can give some clues as to what it is. Is it that the area was just rice, there was rice paddies and everything was harvested? Is it a gigantic landslide that's moving slowly? What is this process? And so by doing this in really, really complex terrain, it's really tricky because of the characteristics of the satellites and overpasses. And so this is an area that, as Mohang knows, is quite a challenge. And so what we're trying to do is identify some of these moving parts so that maybe we can identify precursors to future catastrophic failure at a specific point. All right, so in terms of synthetic aperture radar, there's a lot of different ways that we can apply this. Slow-moving landslides and also looking at critical failures are some of the traditional techniques, but what we're trying to do is try to see how fast-moving landslides might occur. All right, so I'm going to go into our global model, which is the area that I'm closest to right now. So going back to looking at Earth as a system, we're trying to harness as many different satellite products as we can to provide a relative awareness of potential landslide activity at the global scale. So we're going literally from the hill slope now all the way to the global perspective. And so the approach is a decision tree structure that incorporates susceptibility information with rainfall from satellites to characterize potential landslide activity. And this model is dynamic, providing every 30 minutes. So this model has been developed to provide situational awareness to emergency managers, operational disaster support specialists, NGOs, the World Bank, others, all of whom have kind of taken a look at this already. And so because NASA always needs an acronym, the model is called the Landslide Hazard Assessment for Situational Awareness, or LHASA model. And so again, another chart, but what this looks like is we have different susceptibility. We have different products that are used to calculate global landslide susceptibility. We have elevation, we have faults and geologic reasons. We use a geological map of the world. So, we're really limited if we want a globally consistent map by the quality, as you can imagine. In the geology department here, a globally consistent geological map is not amazing. We have road networks we look at, and we also use forest cover change. We also look at rainfall and validate it with the catalog I introduced at the beginning. So the way that we calculate, I'm going to gloss over this, but the way we calculate susceptibility is using a fuzzy method approach, fuzzy overlay, looking at distance to fault zones, distance to road networks, forest loss, and precipitation, and then ultimately using predominantly looking at slope to create this global map, which looks like that. So this map is available publicly. It's at 1 kilometer spatial resolution, and it's highlighting different areas around the world where we have higher or lower landslide potential based on susceptibility. Okay, so we have the idea of where these landslides might happen, but now we need to know when. And right now we're looking at rainfall-triggered landslides. So going back to GPM that I introduced at the beginning, the Global Precipitation Measurement Satellite, together with about 10 other satellites, is used to combine efforts for a global view of precipitation every 30 minutes around the world. I was going to update the time slice of this, but actually this is from just not too long ago, and it actually highlights when we had 4 different named storms of the Atlantic, and this is Hurricane Florence, and you can watch it as it actually moves over land and ultimately dissipates. And so this data is publicly available. You can see we have both snow and ice as well as liquid precipitation. And so the idea is we can start to understand, here's a super typhoon that you can see hitting Asia. Having an understanding of where our weather is coming from is critical, not just for modeling landslides, but to get a sense for what the distribution of precipitation is prior to a storm making landfall. These types of observations weren't really possible in this way before this type of data sets. So we're using this data. Now, the way that we combined it is we look at the past 7 days of rainfall at every pixel around the world. We apply what's called an antecedent rainfall index. It kind of has a dry down effect in the 7 days based on kind of the soil. It's loosely correlated with data from several different study sites. And then we apply a threshold technique. So we look at the last 7 days of rainfall. If it is above the 95th percentile at each pixel over the 20-year record, then we assign it a high value. If it's low, we don't give a nowcast. If the rainfall is high, we assign it. We look at susceptibility to determine whether or not it's high hazard or moderate hazard. So it's very simplistic. And it's simplistic on purpose because this is used as a situational awareness tool and people really need to understand what it means. So this data is distributed in every 3 hours right now, but we have data every 30 minutes. So right now it looks like this. We're able to identify different reports. That's what the R shows. And the distribution at any given 3-hour period looks like this around the world. But in terms of performance, we're able to see how the probability of detection of a landslide, it can range anywhere from, like, you know, in some cases we're getting 10% of the landslides that we have. In other cases, looking at a temporal window, so looking at the couple days surrounding when the landslide happens, accounting for the questionable reporting times, we can get a little bit better performance. But ultimately, we find that the model performance improves when the quality of our landslide data improves. So what this is suggesting is that while the model's on track, we need better validation data to help improve our model, not just to calibrate it. This data was obviously not involved in the calibration, but in order to validate, better data yields better results. Not rocket science, but yeah.
Kind of confused, I guess. Can you clarify?
Yeah.
When you're saying 1 day moderate hazard, if you say 34%, you're saying that 34% of the time that you predicted a moderate hazard, there was a landslide. Is that how to read this graph?
I am saying that of our global landslide data set, so of the almost 5,000 landslides, that we were able to get 34% of them looking at the moderate hazard category. The 1 day, 3 day, and 7 day. So the challenge is that we have our global database of 11,000 reports, but because we don't always know exactly if it happened that day, the day before, the day after, we give a little bit of a temporal window around that to say it might have happened the day before, might have happened the day after, we don't know. So that's what the 3 day and the 7 day. And that's why obviously the results get better, because you have a longer spatial window or temporal window to look at. So yeah. We also have results really just focused in Nepal, and we use a totally different data set, and the results are like 60 to 70% detection rates. In terms of false positive, that's what the frequency, how often we get them. We have about 1%, I guess, false positive rate. We just don't know. When it comes to this, you don't know what's actually a false positive because maybe it just wasn't mapped.
So I have a question about, I guess, in the previous plot you were showing us, like, in different regions you would map out a time-varying, like, susceptibility to landslides.
Time-varying hazard.
Time-varying hazard.
Mm-hmm.
And here we're talking about true positives versus false positives.
Correct.
How can you compare a hazard to an event? Right, a hazard is you give a probability of an event occurring.
Right.
So how do you get a positive, I don't know how you get a false positive or a true positive when you're not actually saying there will be an event or not be an event, you're just giving it a probability.
So we don't give a probability. Right now it's strictly a threshold by binomial yes-no.
Okay.
So basically, for any given pixel around the world, either you have a moderate or a high hazard indication every day, every 3 hours right now. We either say, yes, a landslide we think is going to happen there, or that there's potential activity there, or no, it's not. And so we take all of those, moderate or high nowcasts, and we see if a landslide did indeed happen at that 1 kilometer pixel when we issue the.
Okay.
However, I have a whole lot of plans for phase 2 of this project, assuming it gets funded. And it will go into probabilistic estimates. It'll also go into forecasting. So not just saying, 4 hours after the fact, we think landslides may have happened here or there's potential activity. But let's look at the 24 or 48-hour forecast. That's also our plans, and several other.
Okay. So within a kilometer space, your model says it will occur today or it won't occur today.
Yeah, there's
or 3
potential
days
for
or
landslide
something.
activity
Okay.
that day.
Okay,
Correct.
and then you validate again. Wow, so the false positive rate then would be where you said there was, but there wasn't.
Right. And my point is, it's really difficult for anyone doing this type of work. It's so difficult because you don't have a comprehensive inventory.
Yeah.
You don't know if it's actually false or not, but we assume that it is because that's what you have to assume. So it's a false positive rate based on just the number of times the threshold is exceeded in any given year.
Okay.
So I'm assuming you've got this database and you have a different threshold for every place in
Yes.
your database based on slope and other characteristics.
Yes.
How variable are those thresholds?
So with susceptibility, so you have a susceptibility value from 0 to 5, 0 being ocean water and 5 being the most, and that process I'm not going to get into, but
But you lump things into fairly big classes.
correct. So it's all categorized. But then in terms of the rainfall, each pixel has a different value for the antecedent rainfall. And based on the 16 or I guess 17-year record that we have from the Tropical Rainfall Measuring Mission, TRMM, which occurred right before GPM launched, we are able to develop a threshold based on the 95th percentile of the rainfall at that individual pixel. So nobody, yeah.
Didn't want to interrupt you.
No, I was, yeah.
So this map doesn't look like topography, but the other map that you showed of the susceptibility,
Yeah,
this one,
yeah.
looks much like topography.
Yes.
So why is this?
Because slope is the most important variable when you're doing landslides.
But it doesn't appear in the other map.
Because the other one's of rainfall.
Okay.
So-
this is what I understand is supposed to be-
Antecedent rainfall index, so it's just looking at rainfall. So it's slope, land cover, all of the different geophysical and geomorphological representations of where landslides could happen, and then the trigger is separate.
Okay, got it.
Yeah, yeah.
Do you see like a dramatic change between the windward and leeward side?
So yes, if we had a higher resolution model, we would. However, our model's at 1 kilometer, and so there's a lot of challenges to that, but we do not look at aspect in the model right now. And because it's at 1 kilometer, that type of, complex topographic features and the relationship between different sides of the mountains won't come out in this type of global model. But if you look regionally or locally, like we've done for Carnally Highway, absolutely, it makes a huge impact. And so aspect is one of the most important, in addition to slope, in identifying potential triggering sides of the mountain, because the rain just kind of keeps pushing into one side of the mountain and misses the other side. Yeah. Thanks. All right, I'll show you some cool graphics now. Oh no, that's not cool. Sorry. Okay, so all right. So average nowcast rate. So what we did was we ran the model retrospectively. We looked at the high hazard model on top. We looked at the moderate hazard on the bottom, and okay, this isn't cool either. And then we were able to overlay that with our global landslide catalog, and we started to identify places where our model indicates that we might have landslide activity, but we don't have any reports. And so there's a lot of different things to unpack here. And I'm just going to go to this because this is cooler. So what you can do is you can first, all of this seems fairly simple, and it actually is. I mean, to first order, there's a lot more stuff that happens under the scenes. But what you're seeing here is actually the landslide climatology for every month. So the average of September's, October's for our whole record. So we have about 17 years to look at when is landslide season around the world. So you're going to see the actual nowcast rate, which I introduced, and now you're going to see it overlaid with our global landslide catalog. And so what you start to see is you can identify areas where, such as the East African Rift Zone here, where you have a lot of potential landslide activity at periods of the year, but no reports at all. And so it's really hard because we know that there should be landslide activity there. We're not the only ones that think that, but we just have difficulty getting data. The same is true for parts of South America and even parts of China, for example. So what are we learning? Because this is all new. This is a new way to look at the data. Landslide season kind of wasn't a thing, and now we're trying to, make it a thing. And so this is just an example of some of the characteristics you can unpack from the model when you look at it in aggregate over almost 20 years. Is you can start to see that, in January, Peru is you can start to see the correlation between the landslide model and the observed landslides over Peru in January and July. Same is true for Southeast Asia. You can start to see these seasonal patterns and distribution of landslide activity across this area. Okay, so why do we care, right? This seems kind of esoteric. I'll be the first to say it. It seems like it's really big picture. Who in their right minds wants a global landslide view of things? Turns out there's a lot of people that want this global view. So I'm going to give you a couple examples. The first is the Army. So we have a pretty close relationship with the U.S. Army Geospatial Center that's actually located in Fort Belvoir. And they provide geospatial information to the different command centers around the world. So wherever they have troops, they want to know what's happening, specifically for hazards. And so what happened here was the El Nino in 2016-17 had a huge impact in Peru. And so we actually provided the susceptibility map. This is before our model actually was fully realized. We provided the susceptibility map to them. They then went and shared it with the Peruvian army, and they used it to brief the ambassador, the US ambassador in Peru. And it turns out they actually found areas that were supposed to be landslide prone that they hadn't really looked at yet, and there actually were landslides there. And so it helped them to really get a countrywide perspective of potential hazard areas. And according to him, he said it's 99% accurate, but I really like that quote. I don't necessarily agree with him, but I think that that's a pretty awesome quote from the Army. All right, another example is Hurricane Maria from last year. And so because we have this data in near real time, and so on the right, what you're seeing is the global precipitation measurement data. So this is Hurricane Maria as it was making its way through. And then this shows what our landslide nowcast looked like. And obviously it was updated every 3 hours throughout the storm. And so what it highlights here is, so this is the same view. This is Hispaniola. And so what you can see is that all of these islands really were having a rough time potentially with landslides, and it even highlights the potential of Puerto Rico for landslides even before the storm made landfall and continued on. And so my point here is that right now it's useful as a real-time tool, but the value of predictive capabilities for this is tremendous. And so what we're hoping to do is be able to provide a 24 to 48 hour landslide potential forecast, which I think is going to be much more valuable to these emergency response groups to prepare for at least understanding where the hazard might be. And then another example, as I said, I just got back from Rio de Janeiro, and Rio has been taking our satellite, our model, and actually inputting it into their Alerta Rio system, a citywide alerting system to identify potential landslide activity and ultimately make alerts. And so we have a formal partnership, NASA and the city of Rio, to look at not just landslides, but look at water and air quality, to look at actually education and bringing Earth observation data into the teachers in Rio and use it in their classrooms. And so this is just an example of what they implemented. So they're using their own rain gauge data, their own susceptibility map at the citywide scale at much higher resolution, but using our dynamic platform to actually make operational alerts of this system. And so as I said, I was just there. This is their center of operations. It kind of looks like, you know, the Houston, the Johnson control room, but it's for the city. It operates all the stoplights. It provides the weather forecast. It monitors any issues throughout the city. And so this is shown right here as an example of one way that they can use geospatial data to better understand what's happening at the city scale. Okay, so going forward, the path forward, I think that this is 1.0, and we're really hoping by next year to be at 2.0. So first, we find that the model struggles in areas with lighter rainfall, especially in areas like the Pacific Northwest, which have a little bit different mechanisms than what this model might be the best at. Right now, the model looks at shallow debris flows for the most part, not these huge deep-seated gravitational slides out west. And so I think there's ways we can improve that. And so moving forward, we are, again, looking at forecasting, looking at kind of more dynamic variables, burned areas, for example, seismicity, as well as moving towards risk and understanding how we can characterize risk dynamically, which is actually a pretty new concept in the landslide field. And then with the last 4 minutes, is that okay? Okay, I want to make a pitch for citizen science. So in terms of a future outlook, there's a lot of things. I mentioned some research projects, if any of them pique your interest, with remote sensing, but this is also something that's been quite grassroots, but we just launched in March, and it's a global landslide citizen science effort. It's called Landslide Reporter. And so if you go to landslides.nasa.gov, you can download all the data I showed, all the global data. You can also have links to the global susceptibility map and precipitation. And so we're trying to lead by example by building a cooperative open online landslide repository, or COOLR. I promised you at NASA, there's always acronyms. So the Global Landslide Catalog is what we've been developing. Landslide Reporter is going to be the citizen science contributions, and then we're also working to bring in other inventories to really have a collective place that we can openly share different inventories, because that is a huge challenge in our field. What the viewer looks like is, this is our data. You can look at what the nowcast, so what I was just showing before, you can look at that for any 3-hour period. You can also look at the base susceptibility map and precipitation and compare all three to understand what's happening. And then with Reporter, you have to log in with Facebook or Google. We don't store anything, I promise. You can submit a landslide based on a lot of different characteristics. You only have to really include the source of the information, but we'd love for you to fill in more information. And so then once that data is submitted, we submit we validate it at NASA to the best that we can, and then it becomes part of the global database. So if you have some time on your hands, if you want to work more on this, if you're good at so it's all built on Esri mapping platforms. If you're good at web app development in terms of Esri mapping, really interested in talking to you, because there's a lot of different things that we can do with this. As I said, it's just gotten off the ground. So concluding slide is, if you're interested in getting involved, we have postcards. It's an area that, we'll see where it goes, but so far we've had about 100 contributions from 25 different countries. So that indicates that maybe we can start to identify some of these areas where we have biases in our global catalog and start to fill it in with people on the ground who either see landslides or are able to contribute them based on their local expertise. So thank you. Another visual. So thank you very much. Happy to take questions.
Done or considered integrating population density into your models?
So population density is something that we have looked at. There isn't as clear a relationship. Well, let me put it this way. Population density is tricky because our global landslide inventory is highly biased by population centers. So when you start to bring in population, then you start to all of a sudden, it starts to look better, which is not what you want as a scientist. You want to be able to objectively look at each layer. However, when we start to build a risk model, population density is going to be really important for looking at exposure. So the people themselves are not the reason that landslides are being caused. There's some very close relationships when you're dealing with some areas, but we're using that layer as more of the exposure, identifying where people are exposed, trying to keep it separate.
So given global climate change is probably kind of throwing a monkey wrench into all of this, right? Because the patterns of where you're showing right now, the variation through the year, potential landslide activity, are you able to either factor that into your models, or are you seeing the opposite, seeing signals changing from year to year to year that might be related to that change from climate?
So the role of climate change is, this is an area that's also emerging. One of the challenges is that in order to develop a benchmark, a baseline for understanding what might change with landslides, you need a really long record. You need more than like 10 years. You need 30 years at minimum. We don't have 30 years. However, what we have done, and this is new research I'm not showing because we haven't published it quite yet, but hopefully soon, is that we actually took our global model and we're working with people at NOAA to apply an ensemble of their global climate model. We looked retrospectively to match it against our data, and it actually looked pretty good. So we looked in Nepal and we ran it to 2100, and what we actually found was there's going to be, as far as we know, changes in the extremes. So in the tails of the distributions of precipitation, there will be an increase in extremes, and that translates to potentially changes in areas of glacial lakes and in glaciers. And so just in that little area, that's what we're working on now, and just in that area we can say, okay, well, based on changes in extreme precipitation, we may actually see this very marginal area already be further subjected to potential landslide activity. So we're looking at that. We're also looking at the same patterns in the US. But again, it's really in order to really, really trust it, you need like a 50-year record of landslides. Nobody has a 50-year record of landslides. So in lieu of doing dating on every single landslide, which nobody's funding, we're trying to have these proxies using models and validate it, 10 to 20-year time scales. Yeah.
I wonder how you're going to deal with the kind of trigger mechanism for the deep-seated slower moving landslides. Are you going to use sort of a cumulative precipitation?
Yeah.
Have it constantly being updated?
Yeah, no, absolutely. I mean, we've been looking in the Pacific Northwest, and I mean, really it's seasonal precipitation that is causing that. So by looking at 7 days, you're not getting at that. However, in the future, it's not in phase 2, but I think in maybe phase 3, the kind of 2-month-long, 3-month-long cumulative precipitation, I think we'll get more at that. But then you're dealing with, what is the depth of the soil? What's the depth to bedrock? What's the water table look like? And those are all potentially modeled parameters that we have at NASA. How good they are, I don't know, but we do have models that look at water table depth and some of those more hydrologically focused parameters. And so we really want to get into that, I think, in the next phase of our research. Yeah.
Have you thought about integrating seismic hazard into your landslides and seeing if maybe potential for aftershocks causing landslides?
Yes, definitely. So again, a proposal that we have that's hoping is successful is that we would like to couple rainfall-triggered landslides, our model, with a co-seismically triggered landslide model. So when an earthquake happens, based on the type of shaking, right, you're going to have distribution of landslides in entirely different patterns than that of rainfall-triggered landslides. Landslides that are triggered by earthquakes tend to happen at the ridge top, so they shake and then everything falls from the top, whereas with rainfall-triggered, they tend to happen kind of further down on the slopes. And so integrating those two is an area that we really hope to get into. We just haven't gotten there yet. And those communities, by the way, we don't really talk, so I'm hoping this proposal is also teaming with a group from University of Michigan that are excellent in co-seismic landslides. So, yeah, talk to me next year. Hopefully, yes.
Just as a follow-up to that question, actually, so I think all of the data that you're working with is all remote sensing data, right? So,
well, some, yeah.
So, in fact, there can be coupling between the landslide and the solid earth itself, which can result in seismic waves. And it depends on, the exact type of wave and how much excitation of seismic waves happen depends on the mechanism of the landslide itself. Mm-hmm. So there was a paper in 2013 by Ron Ekstrom looking at this.
Yeah.
So I was just wondering if you have looked at correlation of trends between the potential activities versus some kind of seismic-driven detections.
Yeah, we were actually talking about that earlier. Yeah, looking at seismically detecting landslide movement is not an area that I actually went to grad school, and I wasn't working with Ron, but in the same place. That is not an area that we've looked into thus far. It's kind of a totally different observational mechanism, and it's definitely an emerging area of research, and I'd love to see what comes out of that. I think the challenge is that they tend to be really big. You can only do it if it's really, really big. And if it's really, really big, then we probably see it from space, or you hear about it sometimes, depending, unless you're in Myanmar or Alaska where you have these huge complexes. But then it doesn't hurt anybody. So it's this weird dynamic, right? We want to kind of identify landslides in places where people are most at risk to them. And so, I don't have any plans to look in that, but I'm definitely following the research for sure.
Just to calibrate, maybe going into the past, for example.
Yeah, it could be. Again, we're looking at the big events, but that's, absolutely, to look at least that record to see when they happen. Mm-hmm. Definitely.
Hi. Actually, it's really interesting to look at the table where you have the success rate.
Oh, okay.
What I notice is that your moderate hazard compared to the high hazard. Yeah. It seems to systematically success rate is higher. Yes. For the moderate hazard than the higher hazard. Can you comment on that? Is this something that's your model that's predicted this? Would built in that for the high hazard is less
So it's actually very simple. So the moderate hazard looks at susceptibility, where it looks at areas where susceptibility is moderate to high, and high hazard looks only at very high landslides. So there's just a lot more surface area to consider. So we have, for the moderate hazard, we just have more area being included in that analysis, and we have a higher hit rate, right? So a higher false positive rate potentially. So with moderate, you have a larger area to have in your potential detection. And high is just looking at the very high susceptibility classes. You just have less land area in those zones. It's really, yeah. So I don't know if, I mean, it goes back to how do you categorically define susceptibility from 0 to 5, right? What does that mean? And we have a whole paper describing it, but everybody kind of somewhat, in some subjective way, picks those categories. And so again, in phase 2, man, I need to come and give a talk next year, and hopefully I've made good on some of this. In phase 2, the hope is that we move from that categorical representation of susceptibility to a probabilistic one, because that makes a lot more sense. And I think that it makes more sense to responders too, to have kind of you have a 50% probability of landslide activity versus like a moderate, I think that's where we want to go. But again, it takes a little bit of a different model, and it takes a lot better data. So we're moving forward in both of those areas.
I guess we have the last question.
What's up with the UK?
What's up with the UK?
Yeah, if you look at your reported landslides, there's a lot of white dots there, which means no casualty, but somebody reported a landslide.
Yes.
I thought originally just because the language is in English,
Totally.
but in your hazards map and nowcast,
Yeah.
it never leads up.
No.
There's never any things that should be happening in the UK. Yes, you have all these reports. So
Yes.
what's up with them?
They complain a lot. No, I'm just kidding.
That would be nice, actually.
No, honestly. Right now, we focus on English-speaking media, and the UK is excellent at reporting landslides. I mean, they still have topography, right? They have little cliffs that block landslides, and the US does too, right? Anytime there's a landslide that blocks a road, at least some news source complains about it, right? And the same is true in the UK. So by and large, the distribution are from English-speaking, well-represented in terms of media sources, right? So there's total bias, we've shown that. And now we need to figure out how to improve some of the area in terms of cataloging, improve some of the areas where we just have nothing. Like apparently a researcher in Macedonia wrote us and said, you have like 3 landslides in Macedonia. I have a catalog of 200 landslides. Would you like it? We said, yes, please, right? What's happening in Macedonia? I don't know. Once I looked at where Macedonia was, we noticed that, there should be landslides there. And so they helped us figure that out.
Okay. Just a very quick comment. So if you guys are interested in translations undergrad, if you can help her, maybe you can translate the website to different language.
Yeah.
You may help other community to report their landslide schedule. And I think I have a 300,000 landslide map of Taiwan.
Sure. Well, it's interesting. But if you think about it.
30,000, sorry. Not
I think the challenge is is that we not only want to know where they're happening, but when. And once you ask when they happened, it gets a lot more complicated, because a lot of the inventories, they map an area and they're 1,000 landslides happened in this quadrangle. And you're like, great, but when? Because I can't validate my model against an inventory I don't know. So it's important for static representation, but for understanding kind of dynamic hazard, it's limited. I'll still take your data, don't worry.
Time for each answer is
Perfect. Yeah, let's do it.
Okay, so I think we can bring the rest of the conversation back to a geology launch, and let's thank the speaker again.
Thank you. I have postcards.